Hello folks, it's Professor Fiore, and today we are going to answer the question, can you make a differential amplifier using JFETs instead of bipolar junction transistors? In other words, something like this. Well, the quick answer would be, I think so, because otherwise I wouldn't be doing a video on it. But let's take a little deeper dive than that, shall we? All right. If you haven't taken a look at the videos on differential amplifiers, you should do that before we look at this. I'm using a circuit that's very similar to the one we created with some BJTs. I've modified some of the resistor values, but I'm using the same high quality current source, tail current source that I used in that video. The big difference here is that I have replaced the transistors. I had some 3904s in here with a couple of JFETs. I've also managed to increase the resistors out here, the gate resistors. We had much smaller base resistors in the BJT version, and I can also compensate by having much smaller capacitors, C1 and C2. The rest of the circuit is very, very similar. Now, I'm not going to say that the performance is going to be identical between the two. It's not. It's definitely not identical. The big advantage of using a JFET for the diff amp is huge input impedance, right? You would never have 22 megohm resistors out here for base biasing resistors with BJTs. That ain't going to cut it. But it's no problem with the JFET. All right, when did these things first come out? Well, back in the, I think it was the maybe mid 70s, 1970s. Back when I was just a little college student, a couple of companies, National Semiconductor and Texas Instruments, came out with some op amps that were called Bi-FET op amps. So there was a combination bipolar and field effect. And they had JFET front ends. They had a JFET diff amp. Now, there's a plus and a minus on these things. Those particular op amps, what I would refer to as the Gen 1 of Bi-FETs, they had good slew rate. They had some, other good parameters like the gain bandwidth product, but their DC performance, like their offset drift performance, wasn't quite as good as the standard all bipolar designs at the time. But they did have this amazingly high input resistance. All right, now those part numbers. On the National Semiconductor side, it was the LF351. On the TI side, they had the TL071 and the 081. And they also both companies made duals and quads. So you could get, along with the 351, you could get a 353 or a 347. And on the TI side, you could get a TL072 or 82 and an 84 or a 74. All right, so those were pretty popular op amps. They had same pinouts. They're still available. You can still find those. These days, I would use the next generation up. If I had an inkling to do something like that, I would, instead of using, say, a 351, I would reach for an LF411 instead. The DC performance, like offset and drift, is much better, and the AC performance is similar. But in any case, I digress. Let's take a look at the performance of this, right? Where are we? Well, for our model data from the simulator, I'm going to pull off some values. GM0 is 3.17 millisiemens, and the VGS off is a negative 2.88 volts. Now, this brings up an important point, which is on the simulator, these two transistors are identical. However, if you were just to go out and grab a couple of 2N5458s, they're not going to match super well. In the simulator, it's the same model, so they're going to match perfectly. But this is an issue with discrete JFETs. If you're going to do an integrated design, it's easier to get better matching. Whenever you do any kind of integrated circuit where you've got a couple of transistors, they're sitting right next to each other physically on the same piece of silicon, you can get really good matching that you won't get by just pulling discrete components out of a bin, and trying to sort through them maybe. It's really difficult to get that kind of level of matching. So this is kind of a best case, right? Putting it in the simulator is sort of a best case. But nonetheless, the way we have this biased is with this little tail current source. This utilizes a Zener diode. This is a 5.1 volt Zener diode. So this 1K up here establishes the Zener current. We can ignore base current for the most part. So 5.1 minus 0.7, or 4.4 volts, drops across the emitter resistance, which I'm calling our tail, 1K. So 4.4 volts, 1K, we should get 4.4 mils, right? 4.4 milliamps coming out through here. And that will split because everything is ideally matched, right? That'll split. So we get 2.2 mils on each half, right? 2.2 mils here, 2.2 mils here. You pass 2.2 mils through these drain resistors, and you're going to get, 16 and 18 and change. Let's call it 18 and a half, round it off. So from the 25 volt power supply, you're looking at maybe 6.5 volts DC sitting on the two drains, right? Thereabouts. So let's do a little DC analysis over here. See what we get. All right, so like I said, pin 7 and 8 should be sitting around 6.5. Okay, 6.541. All right, that looks good. Those currents, like we said, were 4.4 on the tail and about 2.2 on these two. So let's see, we're getting 2.251. All right, on this one, and I'm sure the same on the other one. Yep. So that looks good. The tail current down here is a little over the 4.4, so we're getting 4.5. In fact, I'm going to guess the Zener. Yeah, the Zener is a little over 5.1. We get 5.2 on the Zener. All right, so, bottom line, that looks pretty good. All right. So, like I said, because this is perfectly matched in the simulator, we get this perfect matching on the two drains. If you built this in lab, don't expect that to happen. Don't expect that both transistors are going to have identical VGS off values and identical IDSS values. You could go through a whole bunch of them and sort them and get a better match that way, but that's not really the point. That's not really what I'm going after here. Let's take a look at the gain. The bipolar on this has a sizable voltage gain. What do we have here, right? So we've got an idea on the DC. Now I'm going to need to find the GM value in order to find gain. So let me just pull some things up here. So off of the data sheet, which is actually the model values for these guys in the simulator, we can calculate IDSS using this equation based on these two numbers, and we get about 4.5 milliamps for IDSS. Now, given that, because we know the tail current is about 4.4 mils, and we're getting 2.2 mils in each half, we can just take that ratio, 2.2 over the 4.56, in other words, ID over IDSS, that gives us 0.48, and we know that the ratio of GM to GMO is correlated to the ratio of ID to IDSS. In fact, GM over GMO is equal to the square root of ID over IDSS. So we can just use this bottom equation. GM0 is 3.17 millisiemens. The ID over IDSS is 0.48, so take the square root of that, and our GM comes out to 2.2 millisiemens. Now I can use that in the next step to find the gain. So just make a note of that, all right? Now we have to go and figure out what the gain equation is for the JFETs. Well, in the bipolar situation, you remember that, looking at one input here, that same collector inverted, the opposite collector, all right, just pretend there's two BJTs here, the opposite collector was in phase, right? So this was inverted, this was in phase. The same thing is going to happen here. In the bipolar, this was a swamped common emitter amplifier, basically. And going in this path, you had a follower, right, a common collector, which then fed a common base. Now, neither the follower nor the common base are inverting, so that's how we got the same phase out here as we had on the input. So the same thing is going to happen here, a very similar sort of thing, I should say. Here we have a swamped common source when we're going from this gate up to this drain, And going on the lower path, this is going to be a source follower, a common drain, and coming in here is going to be a common gate, right? So we've got a common source configuration, and then going this way, we have the common drain feeding the common gate. So let's take a closer look at that, all right? Kind of like this. So I'm more interested in what's happening out this way. We're going to need to know what the impedance is from this point. In other words, looking at transistor 1, from its source to ground. What is that? Now, I've just thrown in a sizable number, 100K, for the resistance value of the current source. In other words, the tail current source with the bipolar. I'm just throwing in 100K here. I don't really care what it is. It could be 50K, it could be 500K. As you'll see, it's not really going to make much difference in the real world. So anyway, here is our follower, and here is our common gate, right? The source terminal for this device is right here. So looking up here, if you haven't watched the common gate video, I'll run through this real quick. To find the impedance looking into the source of the JFET, what we do is we just do an Ohm's law. We say, well, what's Vin divided by In? By definition, that has to be Zin, right? So I'm looking into the source. So what is the voltage that we see? Well, it's basically VGS. What is the current coming in? Well, that's the current ID, right? Source current and drain current and FET are virtually identical. So we just make that ratio. Vin is VGS, and then In is ID, but ID is equal to GM VGS. So we have this expression here. The VGS is canceled, and we find out that Zn, looking into the source, is simply 1 over GM. Now, if these two transistors are matched, this GM and this GM are the same, right? That's what we're looking for, matched devices. So I don't really care what that number is, but we know from preceding work in small signal transistors, GMs might be, a few millisiemens. So a reciprocal of that, we're talking hundreds of ohms. That's why I don't really care about the exact value of the internal resistance of the current source. Whether it's 100K or 500K or 50K, it's going to be in parallel with this Zn source, which may only be a couple hundred ohms. So it's not really going to have much of an impact. It's really just the 1 over GM. We can approximate the Zn source as 1 over GM and be done with it, right? So, okay, that's what this is. Well, that value becomes the swamping resistor, if you will, for this transistor when we're looking at its drain, in other words, the common source configuration. So we come over here and we look at the 3 gain equations that we have. We have the swamped gain, right, for the common source. We have the common drain follower, this part going this way, and then finally the common gate from here to here. So looking at the same collector, the same drain, we have inverting gain GMRD over 1 plus GMRS. Okay, so GMRD divided by 1 plus GMRS. But RS is the, what we've called in the past the swamping resistor, the AC resistance sitting out here in the source. But we just said that's equal to 1 over GM. So down in the denominator, we have GM times 1 over GM, which is, of course, 1. In other words, the gain is GMRD over 1 plus 1, GMRD over 2. We get this, GMRD over 2, right? It is, in fact, inverting. We'll take care of that in a sec. Looking at the lower path, this way, the follower is GMRS over 1 plus GMRS, but the same thing, RS is 1 over GM. So in the numerator, it's GM times 1 over GM, that's 1. In the denominator, it's going to be 1 plus GM times 1 over GM, so that's 1 plus 1 is 2. So that's 1/2, right? Exactly 1/2. We see the same kind of thing happening in the bipolar version. We get that gain of 1/2, all right? Now, come down to the common gate. Whatever this input signal is, it's just GMRD. So the whole path is 1/2 times GMRD. In other words, is also GMRD over 2. It's the same. The only difference is this path is non-inverting. This path is inverting. Right? Now, I haven't drawn a 22K load like I did over here for this side because we're just using a single-ended output. But if you had it perfectly matched and you were doing a differential output, you would get exactly the same gain, right? The important thing is this is what you're going to see because, ultimately back here, right, I wouldn't be shorting this input. I would have another input. So, we would still, this would be the same collector, right? Excuse me, I keep saying collector, I mean drain. This would be the same drain, kind of like looking this way over here. I'm looking this way over here, right? But because it's perfectly symmetrical, I really only have to look at one of the two inputs instead of doing it twice. Yay, save some time. All right, so we know the gain is GMRD over 2. That's the magnitude of the gain. All right, I know the GM is 2.2 millisiemens, right? It's basically half of our, well, 2/3 of our GM0, right? The 3.17 that we had because of where we're biased. We're biased fairly well up. We're halfway up the curve, right? 2.2 mils out of 4.56. In any case, we have a GM of 2.2 millisiemens. Do we know what the load is? Well, it's just these two things in parallel, right? 8.2K in parallel with 22K. That's going to give us around 6K. So I can just multiply that out, which I've already done, big surprise, right? And take that 6K, 2.2 millisiemens, divide the result by 2, we get a gain of 6.6. So whatever my input is, which I've set up as 100 millivolts, I should get 6.6 times that at the load, if everything's perfect. Are these numbers exact? Oh, probably not, but we'll see what we get, all right? Let's do a transient analysis over here. Ba-ding. All right, so we're expecting with 100 coming in, we're expecting about 660 coming out. And let's get our legend over here. So here's our generator or input signal. And you can see this is the 100 millivolts, right? There's 100 right there. And here's our output. We're getting 600 milli. So we're getting a gain of 6 instead of a gain of 6.6. But notice here we are on the opposite drain. It is in phase. So that part is working. Everything actually looks pretty good. Other than the fact that the gain is about 10% low, this is working out pretty well. Now the second part of this, of course, is what about the common mode rejection ratio? Am I leading you down a path here just to sort of dash your dreams against the rocks? Are you going between Scylla and Charybdis? Let's find out. Okay, so here's that same circuit, except I've wired the input number 2 back to the first input. In other words, for our common mode rejection test. What do we expect to see here? Well, if common mode rejection ratio is perfect, I expect to see no output, 0. Of course, it's never perfect. It is ultimately limited by the quality, right, for lack of a better word, of this tail current source. What is its internal resistance? The higher that is, the closer to ideal being infinite, the closer it is to the ideal, the better. Okay? All right, and that, by the way, again, I'm assuming that everything out here is perfect. We have perfect match on everything. Because otherwise, even a resistor tolerance change is going to negatively impact the common mode rejection. So let's see what we get. Again, best case, because we're in the simulator and an 8.2K is exactly 8.2K, not like the 8.2K you would pull out of a bin in a lab, right, which has tolerance. In any case, let's run a transient analysis on this. Now remember, before we had 100 millivolts in, we got 600 millivolts out. Okie dokie, what do we got here? Okay, so here's our VGen. Notice there's 100 millivolts, all right? And here's our output. It's really hard to see. So let's go down and change the scale on this. I'm going to bring this down to, let's say, 10 millivolts. Remember, ideally this would be 0. We'd see nothing. Well, even down here at 10 millivolts, so I've zoomed in by a factor of 10, there's still just a little tiny sort of a residual kind of thing. So let's knock it down another factor of 10. So now I'm pushing it down by a factor of 100. All right. And now we can actually see something. So we're getting a few hundred microvolts out of this. All right, we can get a probe on here and get some accuracy on that. All right, we're getting 353 roughly microvolts. And for the in-phase signal, we were getting 600 millivolts. So a factor of 2,000, roughly, nearly a factor of 2,000. Well, that's not a huge common mode rejection, but it's not bad. I mean, if you really need something with a very high input resistance, high input impedance at low frequencies, hey, you can do this, right? I mean, companies do this. You can buy these op amps. This is how it's done. I will reiterate, you build this in lab and the practical problem is getting a good match on the FETs, okay? But it can be done. In the integrated circuit, you have the same piece of silicon. The matching on these parts is going to be very good, all right? Okay, so I hope that answers any questions on using a JFET for a diff amp. It can be done. It has been done. There you go. See you next time.